In the last set of notes, we saw that the rate of change was always directly proportional to p. So we ended up having this differential equation, which always had the same solution. So we ended up with this exponential growth or decay, and it was pretty easy to solve. But what if it says something just a little bit different? So what if it said that the rate of change is proportional to p minus some n value? Well then, dp dt would be proportional, some constant, times p minus n. And we'd have to solve that differential equation. Well, that would be dp over p minus n equals k dt. Take the integral of each side. Our variables in the denominator, so that would give us technically natural log of the absolute value of p minus n, but we'll take the positive version, equals kt plus some c. Again, we'd use exponentials, so p minus n would equal e to the kt plus c, which, remember, this would be e to the kt plus e to the c. Oh, that's a c, not an e. That would give me p minus n equals e to the kt, e to the something, which would give me that constant. Therefore, p would equal e to the c, kt plus n. I mean, we do the same thing each time. So if this one was n minus p, it'd be k times n minus p, and then we'd solve it. If it's proportional to the square root of p, we'd have dp over dt equals k times the square root of p. Inversely proportional would be k divided by p, and so forth. Let's see how a problem would really be asked, to see how it works. Suppose you fill a tall cylindrical can with water and punch out a hole near the bottom. Boop. The water leaks out quickly at first, then more slowly as the depth of the water decreases. The rate at which the height of the water, so rate of the height, changes is directly proportional to the square root of the height. All right, so the rate of the height that's changing with time is directly proportional to the square root of the height. That's the big part we want to get out of this. Now, everything else we can use differential equations to figure out the equation, all of that. It really depends on what information is given to us. They tell us that at time equals 0, the height is 20. That gives me my initial value, which is good. But they also give me the rate at that initial time. That's awesome. So that means the rate when the height is 20 is 5. So I can find k much faster. That would be k, whoops, that's negative 5 because it's falling. Sorry, missed that. Would be negative 5 over the square root of 20. Awesome. Now let's go back. So dh over dt equals negative 5 over the square root of 20 times the square root of h. I want to make that h to the 1/2. That'll make it better. Now, when I rearrange that to be able to solve it, I'd have dh over h to the 1/2 let's make that h to the negative 1/2, equals negative 5 over the square root of 20 dt. Take the integral of both sides. Shoop, shoop. Integral. Okay, I remember how to do this. Add 1 to the exponent, divide by the new exponent, equals negative 5 over the square root of 20 t plus c. All right, okay. So I'm going to have to rearrange that a little bit. That's going to be divided by 2, so h to the 1/2 equals negative 5 over 2 square root of 20 t plus c divided by 2, but that is still c. And that's really square root. So if I square both sides, I get that. Now, let's use that initial information to actually find c. Well, it says, let's use a different color, that at time 0, the height is 20. So, height is 20 at time 0. Well, that's going to be super easy, because that's going to go to 0, so that's going to give me 20 equals c squared. So c is the square root of 20. So let's write that equation out. And I might end up needing to pretty up this a little bit. Let's see, I think square root of 20 was 2 root 5, wasn't it? All right, so this is going to be negative 5 over 2 times 2 root 5 plus c, which is 2 root 5. All of that squared. When I square that, I'm going to get 25 over, oh, maybe I should have left it. That's, that would have been 4 times 20, that's 80. Minus 2 times these two together. Plus that squared, which, oh, that would have given me 20 back. I should have left it, because look what happens. Whew. And 25 over 80, I believe that's 5 over 16 t squared minus 5 plus 20, 5t plus 20. And when is the can empty is the second question. So we can actually set that equation equal to 0 and solve it. Do we need to see that? I'll show it. So if we're finding when it's empty, we're going to find out when this equals 0. So let me multiply through by 16. That's plus 320. I'm going to divide by 5. Oh, that's nice. T minus 8 squared. So at t equals 8. Awesome. A curve passes through the point 0, 10. and has the property that the slope of the curve at every point is twice the y-coordinate. This is more of what I've seen. So, slope of the curve, that's dy dx, equals twice the y-coordinate. What is the equation of the line? So, rewrite. Take the integral of both sides. And I get, oops, natural log of y equals 2x plus c. Y equals, and we know what's going to end up happening. It's going to be c e to the 2x. And we know it passes through the point 0, 10. So the y value is 10 when x is 0. So c is 10. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and the outside air. Suppose that a pork roast is taken from the oven when its initial temperature has reached 160 and is placed on a table where the temperature is 75. Let R be the temperature of the roast T minutes after it has been taken out. So let's back up. The rate of cooling of the object, so dr dt, is proportional to the difference of the temperature of the object and the outside air. Well, it says the outside air is 75. Rearrange. Take the integral. Rewrite as an exponential. It's going to end up being a c in front. kt. So, r equals some value e to the kt plus 75. Well, let's see what we know. The initial temperature was 160. So when t equals 0, the roast is 160. So 160 equals c times e to the 0 plus 75. Let's do 160 minus 75. And I get 85 equals c. So my equation is r equals 85 e to the kt plus 75. So that's the general solution for the situation. If the temperature of the roast is 120 after 30 minutes, what is the temperature after 45 minutes? So T was in minutes, so that's good. So if the temperature is 120 at 30 minutes, 120 at 30 minutes, that'd be 30K plus 75. We're going to be able to find K now. 120 minus 75 is 45 equals 85 e to the 30K. 45 over 85 equals e to the 30K. Natural log of 45 over 85 equals 30K. So K is, let's see, natural log of 45 divided by 85 divided by 30 gives me negative 0.0212. Now I can plug in the 45 minutes. So they wouldn't need to see all of that. They would just need to know that we're going to do R of 45 is approximately 85 e to the, and our K is negative, actually I'll just grab it, times 45 minutes plus the room temperature. And I get 107.742. When will the roast have cooled to 90 degrees? Easy. We're just going to figure out when the roast is at 90. Now we've got our K. And all we have to do is solve that. So I'm going to do it. And you can check your answer. I got, drum roll, 81.821 minutes. Last one. Ooh. Fish are being introduced into a man-made lake. The change in the rate of fish is directly proportional to 900 minus F. I don't even know where they get this stuff. Okay, so DF, D fish, with D time, equals K times 900 minus F. Rearrange. Take the integral. Rewrite. Make that C in front, which gives me, oh, let's see, I'm going to have to rearrange some stuff, huh? You know what I forgot about? I'm going to back up. We need this to be a positive. How can I rewrite that to make F positive? I wasn't even thinking. I suddenly went, that's weird. I shouldn't have a negative F there. Well, if I factor out a negative 1, then I've got this in the right form. I can't believe I made that mistake. Did y'all catch it? I hope you did. Integrate. Now it works. That's much cleaner, isn't it? That works better. Now we can use our initial information. At time 0, there's 400 fish. Well, that's helpful. 400 equals C e to the negative kt plus 900. Oh, 0. Oh, so that's going to be a 1. So C is negative 500. So now I've got F equals negative 500 e to the negative kt plus 900. Now let's use the next piece of information. 3 years later, there are 600 fish. Three years later. So I can solve for K. So 600 minus 900 divided by negative 500. It's going to give me 0.6 equals e to the negative 3k. So natural log of 0.6 divided by negative 3 is going to be my k. natural log of 0.6 divided by -3 gives me a K value of 0.1703. So here's my official equation. C was -500, e to the negative 0.1703t plus 900. Find the fish population in another 3 years. So that means total of 6 years. So you would just plug in 6. So -500, whoops, e to the negative 0.1703 times 6 plus 900. I got 720 fish. What would be the limit as we approach infinity? So what happens here as that approaches infinity? Well, since it's negative, that's going to get really super small. It's basically going to go away, and we're going to be left with 900 fish. That's actually the mass capacity. That would also be our horizontal asymptote.